This video is going to cover the very unique Hamilton-Sangamo master and secondary clock system. The unique part about this system is that the slave clocks can actually run independent of a master clock. They are actually a Sangamo self-winding electric clock. As such, they have the unique feature of being able to run for up to 24 hours during a power failure. Once the power was restored, the clocks would wind back up and they would be ready for the next power failure. These clocks were very reliable as they had no electric contacts, and they were extremely easy to set up as there was no pendulum or the clock did not need to be put into beat. They had a 7-joule lever escapement platform and were basically a giant railroad pocket watch. Sangamo guaranteed these movements, when properly adjusted, would be accurate within 30 seconds a week. Because of this reliability and accuracy, Sangamo clocks did not require a master clock to synchronize the time on every hour. Instead, it could be done once a day, once a week, or even once a month. It was strictly up to the operator of the system. This brochure was printed in February of 1929. However, in May of 1929, Hamilton and Sangamo joined forces in the clock sales business. That is why every slave clock or master clock you will see will say Hamilton-Sangamo on the dial. This system is referred to as the Generation 1 system, as it was the first system manufactured by Hamilton-Sangamo. There were later modifications to both the slave clock and the master clock that were substantially better than this system. However, those will be covered in another presentation. The next 4 slides detail the remaining pages of this brochure. If you would like a hard copy of this brochure, please go to our website, www.sangamoclocks.com. The key paragraph on this page discussed the master clocks available for the system. One was an electrically wound 11-joule Sangamo master clock. Another pendulum-driven master clock was available. However, none of these have ever been found or are known to have survived. This page details the resetting system in the slave clocks themselves, and it shows the gears and wheels and reset levers involved. It also discusses that the clock could be reset from a simple switch, and a master clock was not necessary. This page highlights the wiring of a master clock to the slave clocks on a Sangamo system. It shows that 3 wires are required to be run to each slave clock. 2 wires are 110 volt AC, plus and minus, and the other is 110 volt minus that is supplied through the mercury tube to the reset motors of each slave clock to synchronize every clock on the system. You can see by this diagram, if you substituted a simple push-button switch instead of the master clock and mercury tube, that an individual could push a button in a main office using his pocket watch or sound from a factory whistle and reset all the slave clocks on the system. This last slide shows the pricing of the slave clocks to both jewelers and customers. The top section is aluminum case models, the bottom section is wood case models. And if you look at the column of 1 to 5 units, you can see that $45 for aluminum cased and $55 for wood case models was quite expensive, considering that a car in 1929 cost $300. This was double the cost of any other slave clock on the market at the time. Sangamo slave clocks can readily be identified by the ID tag attached to the back of each clock. It holds 3 pieces of information: the serial number of the movement, which is also stamped onto the front plate of the movement, the type, in this case S for slave, and the style, which is the model of the clock, slave or not. This is a picture of 4 Generation 1 slave clocks that I've wired into one system. There is no master clock on this system, just a push button that I use to actuate the clocks for 15 seconds, which is the minimum time period that it takes for them to complete their reset cycle. This is a front view of one of the Generation 1 Sangamo slave clock movements. You can see the beautiful 7-joule Hamilton platform with a micrometer adjustment, as well as all the gearing that operates on the front of the movement to reset the hands. This is a rear view of the Generation 1 movement. The motor on the left is the winding motor for the mainspring and is controlled by a braking system. The motor on the right is used to operate the resetting mechanism. Between the two motors, you can see a small sub-seconds hand that was used to time the movement precisely at the factory. This slide shows the three main components of the reset system: the two wheels, which hold the reset pins, and the cannon pinion, which holds the reset arm. This stop wheel is used to stop the reset system once it's completed its cycle. It is pushed into place by one of the reset pins and then blocks that pin as it comes around to arrest the inductive motor. It is pushed out of place by the reset arm so that it will allow the clock to complete a reset during its next cycle. This is a picture of the reset pin in the retard wheel. If the minute hand were at 5 minutes after the hour and the train were activated, this would rotate in a clockwise motion, and it would push the pawl backwards so that it would move the hand back to the 12 o'clock position. This is a picture of the reset pin in the advance wheel. If the minute hand were 5 minutes before the hour, this wheel would operate in a counterclockwise rotation, and it would push the minute hand forward to the 12 o'clock position. This small gear is driven by the electric motor on the back of the clock through two other gears to supply power to the reset mechanism. This is the star wheel or stop wheel in its installed position on the front of the clock movement. This is a picture of the star wheel in its locked position where it's just stopped the reset cycle. You can see the tip of the star wheel is resting against one of the reset pins, which has stopped the system, installed the inductive motor. This points out the reset arm located on the cannon pinion. It is actually impacted by the reset pins on both the advance and retard wheels, and also acts on the star wheel itself. This picture shows the reset arm pushing the star wheel out of position of the reset pin on the advance wheel. This is done at approximately 15 minutes till the hour, so this frees the train so the motor can be turned on again during the next reset cycle and the system will operate. This slide shows that the reset arm on the cannon pinion has now pushed the star wheel clear of the reset pin on the advance wheel. Now, if the motor is energized, the system will complete a reset cycle. At the same time the advance wheel is turning, the reset pin pushes the stop wheel back into position, so it will arrest the motor once the cycle is completed. With the tip of the stop wheel now pushed out of position by the reset arm on the cannon pinion, the movement can now complete its 15-second reset cycle when the motor is energized. This video shows a system going through synchronization. Please note that the minute hand must be within 8 minutes before or after the hour for the system to work. This is a picture of the switch box I constructed to simulate a master clock signal for system reset. Coming in one side is 110 volts AC plus and minus. There are 3 wires coming out the other side. 2 are 110 volts AC plus and minus, and the third is 110 volts negative that is energized when the button is depressed on the side of the box. This wire then supplies power to the motor for the reset mechanism, and it must be held for 15 seconds so that the slave can complete its full reset cycle. This completes my presentation of the Sangamo master and secondary clock system. If you have any comments or suggestions or questions, please contact me. Thank you very much.